Start.
Hello, everyone. I'm Yanhuan Li, a program committee member and an assistant professor at the National Taiwan University. Welcome to the Machine Learning Summer School 2021 at Taipei. Virtually, we're happy to have Professor Csaba Szepesvari to give the first lecture. Csaba is a Canada CFAR chair, the team lead of the foundation's team at DeepMind, and a professor of computing science at the University of Alberta. Csaba is working on developing principled learning-based approaches to AI. Csaba is the co-inventor of UCT, a Monte-Carlo tree search algorithm whose variant is used in AlphaGo. He co-authored 3 books, one on reinforcement learning and another on bandits. Csaba also co-founded the weekly Reinforcement Learning Theory virtual seminar series last year. I highly recommend everyone interested in RL theory to take a look at the associated YouTube channel. Csaba will be talking about large-scale learning and the planning in reinforcement learning. If you have any question, please type it on the webpage, and Csaba will answer them later. Csaba, please start. Csaba, please unmute yourself.
Okay. That's right. Thank you, Yanhuan, for the very kind introduction. So it's a pleasure to be there, although only virtually. And we have 3 hours to make the best use of this time. I encourage everyone to ask questions. I shared my slides in the Facebook group that probably many of you are also a member of, and you should know about this group from the organizers. So you can follow the lectures on the PDF, and you can flip back to the slides. If something is going on too fast, then you have that chance. All right, let's get started. So the title of this whole lecture is Large-Scale Learning and Planning in Reinforcement Learning, but I realized that I'm the very first one at this machine learning summer school who is even talking about things, even talking about reinforcement learning. So I'm going to introduce some foundations at the beginning, and then I will talk about online learning, and then planning, and then function approximation, large-scale learning and planning, and a little bit about batch reinforcement learning. So you should get a little bit of everything rather than just focusing on the large-scale aspects, but the large-scale aspects are also going to take a main stage. So with this, let's get started. So the big goal of the lecture is to help you to gain some understanding of what reinforcement learning algorithms are about, and I will try to do this by conveying some theoretical insights, because I do theory. So the contents is as follows. As I already said, at the beginning, I'm going to talk about some big picture questions of situating reinforcement learning and this talk in the context of other fields of sciences. And then I will talk about the main talk has 4 sections: the foundations, the online learning and planning, and their scaling up to large MDPs, and batch reinforcement learning, and then we can have some Q&A. So big picture recap. In this lecture, I take the viewpoint that reinforcement learning is kind of a subfield of machine learning, although I will question this a little bit. But so RL here really stands for reinforcement learning. This is an often used abbreviation. And ML stands for machine learning. And CS is just computer science. So that inclusion is the most important one. So my view of reinforcement learning is that in reinforcement learning, we want to design algorithms. And that's the topic of computer science as well. And so at this stage, maybe it's worthwhile to recap how we are designing algorithms. What is that we want from the algorithms when we are designing them? I can think about three things. We want algorithms to be general. Who wants a sorting algorithm that only works on arrays that contain almost 30 numbers? Or, arrays that only have, even numbers. You want general algorithms. The second criteria is maybe that the algorithm should work, right? Who wants a sorting algorithm that doesn't sort the numbers, right? So we want sound algorithms that work. If the performance of the algorithm is measured in terms of like the quality of the solution returned, then you want high quality solutions, right? So sometimes you run optimization algorithms and then you want high quality solutions. And also you want algorithms which are efficient. That means that they use the available resources in the best possible way. They don't use too much memory and they don't unnecessarily use compute time. So these are the basic requirements that apply to any sort of algorithm design. And it's good to keep in mind because when we are going to talk about comparing different other algorithms, then these are the criteria that we want to use to compare them. So RL algorithms are a little bit special in terms of all possible algorithms. So a sorting algorithm's input is going to be an array, so take some data. So RL algorithms also take data, but sometimes the data are pretty similar to sorting algorithms. In that maybe the data was generated before the algorithm is run and the algorithm is not influencing what data is generated. But sometimes the algorithm is influencing what data is being generated. And that makes other algorithms really special. And because of that, we'll have to pay attention to this aspect of algorithm design. Now, if you have an algorithm, you fix an algorithm, and you fix a problem instance. So let's say bubble sort and some array, which is the input to bubble sort. Then you can put these together. You can run the algorithm on the instance. And there are two outcomes to this, basically. You can ask, did it work? Like, did we get a sorted array at the end of the day? So, if it's an optimization algorithm, you can ask like, how well did it do in finding a high quality solution? And the other aspect of running an algorithm on an instance is that we can ask how much resources did the algorithm use. So you can imagine that there is the space of all possible instances. And then there are all those instances where the algorithm is correct or it's effective. So these are for a specific algorithm. And then for those instances, you can also measure the resource usage. So then having clarified all of this, the question is, okay, then what is a good algorithm? Let's say, what is a good sorting algorithm? But later on, of course, we're going to ask this question about reinforcement learning algorithms. What makes a reinforcement learning algorithm good? So here, the realization is that, well, we have all these problem instances that we want to run the algorithm against, and we want the algorithm to be good on all of these instances. But if you think about it for a moment, well, this is maybe impossible because if an algorithm runs fast on some instances, maybe it is going to be slow on some other instances. If an algorithm uses less resources on some instance, then maybe it's going to need to use more resources on some other instances. So if you think back about how different sorting algorithms work, you can kind of order the instances based on which instances are preferred by which algorithm. So the point here is that the requirement that an algorithm should be good on all instances, we want that. But this is a multi-objective optimization problem. Every instance is kind of creates you an objective. It creates you a number of how much resources the algorithm used on that instance. And then different algorithms create different orderings on the instances. And then somehow we have to decide which of these orderings do we like. So a lot of times we're going to struggle about figuring out how to solve this multi-objective optimization problem and what measures of goodness do we want to accept when solving this multi-objective optimization problem. So that's kind of like the big picture for algorithm design. And I just wanted to recap that because other algorithm design is not different. It's the same questions arise there. So before we move on, I have to also clarify something about algorithms that have hyperparameters. So I'm sure that you have seen papers about reinforcement learning or deep learning or various machine learning algorithms. And then authors are going to say, we do have these hyperparameters that we can optimize this way or that way. Well, an algorithm together with hyperparameters is not an algorithm. It's a family of algorithms. For me, an algorithm is an algorithm that doesn't have any parameters. Like the parameters need to be fixed, right? Because that's at the end of the day what you can run on instances, right? You can't run a family of algorithms over the instances, but you can put in some hyperparameter optimization algorithm on the top of an algorithm family that has hyperparameters. That gives you a specific algorithm. And then we can talk about how to compare these algorithms. But this is just important to clarify because a lot of times I think that there is some confusion about this. So does it make sense then to even ask questions about algorithms that have hyperparameters? Well, in a way, a little bit, yes. Because if you have an algorithm family which have these three parameters, like let's say the architecture of a neural network, for example, or learning rates or whatever those hyperparameters are, then you can still ask some questions. Does the algorithm have some good members? Of the family of algorithms that you can instantiate by choosing the hyperparameters in a specific way. And then you can also investigate the question of like, how can we design algorithms on the top? So maybe you can view this as breaking up the problem into two, choosing an algorithm which has parameters and then fixing the parameters. But the important message here, the take home, is that the fair comparison only applies if you fix the hyperparameters in some way. So that's like a fully instantiated algorithm. And we can only compare and we can only meaningfully talk about comparing algorithms that do not have hyperparameters. All right, I just wanted to get that out of the way. So the next topic is periodical versus empirical work. And I felt that I should talk a little bit about this because in this talk, I'm going to cite a bunch of theorems. So maybe it's good to situate how theory and empirical work, theoretical and empirical work relate to each other. So let's see. So how does empirical work happen in reinforcement learning or computer science in general? Well, what we do in empirical work is that we use benchmarks to evaluate or compare or analyze algorithms. And then occasionally we modify these algorithms to get better performance on the benchmarks. And then occasionally we also modify the benchmarks to create new challenges when we feel that the current benchmarks are not serving their purpose anymore, right? So this is the cycle that empirical work goes through, right? you're designing algorithms, running them against the benchmarks, changing the benchmarks, and then that's how we feel that we are making progress. So the important thing is that theory works the exact same way, except that you just replace benchmarks with problem classes. So these problem classes are nothing really fancy. It is just like a set of problem instances which are theoretically described through their properties. And then a theoretician is going to use problem classes to evaluate, compare, and analyze algorithms. And they're going to modify the algorithms to get better performance on the problem classes. And then they're going to modify the problem classes to create new challenges when a problem class is fully understood. So the important thing here to realize is that there is a very close analog between work being done empirically and work being done in a theoretical manner. So now the advantage of doing theoretical work is, of course, that in empirical work, the scope of the conclusions that you can draw is usually fairly limited. How do we know that beyond the benchmarks, you can generalize conclusions, right? Like that on a new benchmark instance, you will get the same ordering, for example, for the algorithms or whatever was the conclusion of the empirical study. Whereas if you do theoretical work, then, well, by definition, you're proving things about potentially infinitely many instances. So that's kind of like really the power of theoretical study. So they can generalize better. But of course, the trade-off is that, well, in theory work, we have to use our brain, and in our empirical work, we can use computation. So we can be lazy, and being lazy is good. Outsource the work to computers. So that's good. So the one final important point is that separate from both empirical and theoretical work to design and analyze algorithms is the work when we are working on an application. When we are working on an application, none of what I said previously matters. What matters is how well on that particular instance the algorithms are going to work. So in a way, the empirical and theoretical work precedes applications. It prepares us to figure out what algorithms to apply in an applied situation. There, we are only interested in one instance. All right. So in the chat, I see that there is one question. Could you see it back a little bit? The picture you showed on the platform is auto. Okay, sure. All right. I'm too close to the screen, so I'm going to sit back a little bit. Just to talk a little bit more about this comparison in empirical work, the unique limitations of that is that, well, it's limited by compute power, the scope is limited, and reproducibility can be hard, especially if code is not made available, and only publications exist, and in the publication description of the details is missing, and the claims are kind of soft in theoretical work. The unique limitations is that it's limited by whoever is doing the theory. Humans are limited, and humans can also be lost in beauty. So maybe you're not working on the most important problems, but you're working on the problems that are the most beautiful to you. And you can also lost in detail. Maybe you try to, sharpen that pencil, and then the pencil is just getting shorter and shorter, and you kind of lost there. So the unique merits of empirical work is that it's widely accessible, and choosing problems, like what problem to work on, is usually more obvious, because it's like everyone understands what they want to do. I want a robot to do this and that, and then I can design benchmarks that are directly aiming at that robotic situation, robot control situation. And with theoretical works, the unique merits are that, of course, if you prove a theorem, then it's going to be a theorem forever. The truth values are not changeable. And you can also prove that something is not possible. And I think that that's super valuable. Just think about how much money you can waste on designing perpetuum mobile, right? Like, since we know that based on the principles of physics that perpetuum mobile is impossible, no one is going to fund effort. Okay, like a few people fund all the efforts, but they deserve it to build perpetuum mobile. And similarly, in theoretical work, once you prove that something is impossible, you have to move on. You have to look for some other problems, because it's not worth trying to find an algorithm which cannot exist, right? Like, you can prove that algorithms with certain properties just cannot exist. And that's a very strong signal that you have to change something. And also, I would say that the unique merit is that theory work is really clear about the assumptions and the limitations. So it's very transparent. So common issue to both empirical work and theoretical work is that people can easily overfit to the problem classes, benchmark sets or problem classes in theoretical work. So that's something to look out for. So in theory work, there are two activities that people do: problem-oriented analysis and algorithm-oriented analysis. And problem-oriented analysis, you take a problem class and you try to understand how difficult it is to solve this problem class. Does there exist an algorithm that solves this problem class in a polynomial time, for example? And then if the answer is yes, then give me an algorithm and maybe optimize the resource uses. So that's problem-oriented analysis. As opposed to this, there is also algorithm-oriented analysis. When you take an algorithm and you ask questions about it: how fast is this algorithm? How efficiently does it use resources? And which instances are the ones that are the best suited to this algorithm? So it's kind of like reverses things, because an algorithm creates this ordering over the instances, and you can study this ordering given an algorithm. And very often, this is what we do, because we're interested in understanding how the algorithms work. So why do theory? Theory is good because it allows you to perform something like a sanity check. So if you're designing an algorithm, you design a shiny new algorithm, you want to know, does it even work? Well, you can run it through some test cases, some benchmark problems, unit testing, that kind of thing. The unit tests for theory are simple instances. And you can take, for example, we'll talk about tabular MDPs in a second. You can take, for example, tabular MDPs, and you can ask whether your algorithm works in the context of tabular MDPs. And you can also do benchmarking with theory. So ask how well an algorithm is doing relative to the competition. Someone's asking whether I said that the DL algorithms cannot be compared easily. I don't think I said anything like that. Can I provide some examples of overfitting in theory? Yeah, what I mean is that if you pick a problem class, then you can push the theory to the limit and start to exploit properties of the problem class that are really specific to the problem class and do not hold beyond that problem class. And if you're thinking about that, the results are going to be applicable a little bit more generally than just to the instances of the problem class, then you could call that overfitting to the problem class. An example of that could be that if you take, for example, finite and bandit problems and stochastic finite and bandit problems, and you start to design algorithms which are asymptotically optimal, then maybe you're overfitting a little bit the problem class, because maybe your goal is not actually bandit algorithms, but I don't know, sorry, not bandit problems, but problems with states, like full-blown reinforcement learning problems, and you just use bandits as an example of a simplified case to study them. And the conclusions that you draw from there may not be applicable to the reinforcement learning case. So for example, the asymptotic theory may not be super useful or insightful because, I don't know, like in this asymptotic theory, some gaps appear, and those gaps tend to be very, very small and not too relevant in reinforcement learning. Okay. So finally, if we're talking about, well, I want to encourage everyone to read theory, at least if you're not doing theory, but maybe you can also do some theory. And when you're reading theory, the important questions to ask when reading a paper is that, what is the problem considered? So hopefully the authors are going to very clearly state what is the problem considered. And then, of course, what are the claims, the results made in a paper? And important, and it's kind of implicit in the context, is actually what is the context in which the results are produced? Why are people asking these questions? That third part is probably the hardest to get. And to be able to get a sense of that, you probably should just talk to the people who produce the results if this is not clear from the paper. All right. So let's move on to foundations. Finally. So the general lessons for this part, which is going to be about a very simple model under which we want to study reinforcement learning, is that at the heart of reinforcement learning is search held by structure. And a second lesson is that with no or very little structures, the algorithms will need to work really, really hard, even if we choose the best algorithms. And so MDPs do give some structure, but more structure is basically needed for scaling up to large MDPs. And this is the main lesson. So what are these mystical MDPs? So MDP stands for Markov decision processes. And here I'm just going to talk, in this part of the lecture, I'm just going to talk about what I call planning. So the simple picture that we have is here. So you should imagine that there is an entity, some people call it the agent, some people call it the learner, but for us it's just an algorithm, it's a planner or whatever. That needs to produce some action. So there are two basic sets, the set of states and the set of actions. So the one entity, let's call it the agent, needs to produce an action, and it produces this action. So that's at time t, it produces an action. You can use the full history, and that goes into the environment. So let's call that the agent. Let's call that the environment. And the environment is going to be modeled as an MDP. So that's the M there. So it has states inside. And so as a result of accepting the action, the environment makes a stochastic move. So that's shown here. So the next state is chosen from a distribution that is a function of both the current state and the action chosen by the agent. And while this transition happens, also a reward is generated. And so maybe I write it here. So the next state is going to be chosen. And there are many different notations. And so here I'm using one notation on that figure. A different notation is shown. So I'm going to stick to this notation that's shown here. So for every state and action, there is a distribution over states. So that's PSA for every state and action. So given a current state, the next state's distribution is given from this distribution. So this P is part of the MDP definition. That's called the transition dynamics, transition kernel. It's a stochastic kernel. This is stochastic transition. And also a reward is generated. So given this, the reward is going to be just R at ST and AT. And so as these rewards are generated, we are trying to choose some way, we're trying to choose the actions in a way based on past information such that the total sum of the rewards is as large as possible. So in this talk, I will mainly focus on the discounted setting, although I will mention the finite horizon setting, which is usually undiscounted. It could be discounted, and maybe we'll talk a little bit about the average cost setting as well, or average reward setting. And so in the discounted setting, you have this discount factor, which is a number between 0 and 1. And the discounted setting is kind of fitting between the infinite horizon undiscounted setting or the average reward setting and the finite horizon setting. The discounting makes rewards observed far away in the future less important to the controlling entity, because this discount factor is taking to the t-star in the t's step. So imagine that you have a trajectory, state action pairs, and then in the t step, there is a transition. So these are the state action pairs. There is an associated reward. And this reward gets multiplied with gamma to the power of t. And since gamma was less than 1, this decays exponentially fast, right? So this figure shows that this is t, and this is just gamma to the power of t, right? So it's the exponential decay. And it also follows that if the rewards are, let's say, bounded between 0 and 1, which is something that we are going to assume in this talk, it also follows that if you're summing up all the future rewards up from some time step h plus 1 onward, then the maximum number that you can get is going to be gamma to the power of h plus 1 divided by 1 minus gamma, right? It's because the sum of the infinite sum of these discounted numbers, when the rewards would be all 1, would be just equal to 1 over 1 minus gamma. So that's where this 1 over 1 minus gamma appears. Maybe I call this tau rather than h to avoid some confusion. And so if tau is really big, then this number becomes arbitrarily small. And so you can also think about that if you're truncating all the rewards after tau time steps, then the total reward that you may be losing is going to be just very small if tau is big enough. And you can actually calculate the first tau such that this becomes smaller than equal to epsilon, some target value. And that's called the effective horizon at the scale of epsilon. So that's the smallest tau such that gamma to the power of tau divided by 1 minus gamma is smaller than epsilon. So that's the effective horizon. That is going to show up a lot of times. So there's the effective horizon at scale epsilon, and we denote that, let's say, with h gamma epsilon. And we also, I'm going to use h just to denote 1 over 1 minus gamma, which is the multiplier here, right? So this is also equal to this gamma tau times h, right? So we need to solve that gamma tau is smaller than or equal to epsilon, and you can solve that, invert that for tau, and that's how you get the value of h gamma epsilon. Okay. So why are we talking about this? Because if you're interested in not acting optimally, so acting optimally would mean that you're getting the maximum total expected discounted reward or return at every state, no matter how you're initializing your process. But we are only interested in getting an almost optimal behavior, in which case the value that the behavior would achieve would be epsilon close, let's say, to the optimal value. So the optimal value here, V star, is just taking the max over all possible policies of the value functions for every state. And if you want to be epsilon close to that, if you're truncating the horizons and you are optimizing for that horizon after this h gamma epsilon, and you're optimal with respect to that, then that would guarantee that you're epsilon optimal with respect to the infinite horizon objective. So some truncation doesn't hurt. And this just expresses where can you truncate if you don't care about losing epsilon on the return. All right, so the big lesson here is that the objective is going to be to find a behavior or policy. So a policy just means a function mapping histories in general, but sometimes we just specialize this to feedback policies, which just map states to distributions over reactions. And so you want to find a policy which at every state delivers the maximum value. Fairly simple. And the big lesson from the theory of MTPs is that it suffices to find the optimal value function, because if you found the optimal value function, then if you are computing a policy with this little calculation here, this policy is guaranteed to be optimal. So if V is equal to V star, then the policy, which is calculated this way, is going to be optimal. So here, this inner product, so this bracket notation here, that stands for an inner product. So PSA is just a vector of values, right? So PSA 1, that's the probability of arriving at state 1 if you take action A in state S. PSA 2, similarly, and so on and so forth. It's a vector of with S components. And so you can take the inner product between a vector, this vector, and another vector or function, if you wish. So this notation just stands for summing over our state of PSA S prime and VS prime. So that's just the average value that you will get if all the future values are given by V. So what this equation in the bottom says is that the optimal policy is going to be one which you obtain if you, for every fixed state, you get the action which maximizes the one-step look-ahead value, assuming that from the next state you can act optimally. So you just have to optimize for the very first step. So for that, you just take the immediate reward for that step. So that's RSA. And then you have to discount because we are using the discounted criterion. And then the future is summarized by the optimal value that you would get if in that state you choose this action. So hypothetically you say, oh, what would happen if I choose this action and then I act optimally? What would be the total value that I can get? So this equation gives you the total value, and then you just say, oh, let's choose the action that maximizes this value, and you can show that this gives you an optimal place. So that's the fundamental theorem for MDPs. So here there are a bunch of questions. So why do we use discounting? So discounting has some neat mathematical properties, and it is also, so finite horizon setting is interesting, but the finite horizon setting is also very special. You can do something called backwards induction. And because of that, it can be misleading just to study the finite horizon setting. So the discounted setting is infinite horizon, which has its own challenges. If you have infinitely long horizons, then somehow the episodes never end. You have to deal with trajectories that never end. If you want to cut trajectories, you have to cut trajectories on your own. So there are all these important considerations that come when working with infinite horizon criterion, which doesn't appear in the finite horizon case. So it's a little bit more challenging than the finite horizon case, but it's not as challenging as the average reward case. So the average reward case would be very similar to what is written here, except that here, instead of this sum, this weighted sum, you would just take the sum up to time t, divide by t plus 1. So that's the average reward. Take the limits as t goes to infinity and take the expectation. All right. Sometimes you take the expectation first. That's kind of the safer option. So there are these variations, but all of that just expresses that you're interested in maximizing the average reward per time step. And you can just write that in a mathematical fashion. And so that is a reasonable criterion, but that criterion has its own problems because if you're designing, I don't know, some algorithm for a robot and the lifetime for the robot is going to be, I don't know, 10 years, then it's not worthwhile for that algorithm to think about solutions to a problem which would take more than 10 years to get to. So for example, you could get an example where for 10 years, the robot is doing something, and eventually after that, it would get to a wonderful situation where it would collect a lot of reward. But unfortunately, by that time, the robot is going to break down. So it's not worthwhile to consider this setting. This is why maybe we are choosing the discounted criteria. All right. So the next question is, so this setting is called the tabular MVP setting, when you have finitely many states and actions. Why should we study this setting? I think it's really important to study this setting because then we're not building on sand. Like we have solid definitions, we have a solid understanding. And if we have an algorithm in mind that should solve, you know, like some larger setting with infinitely many states and actions, at least that algorithm should have a specialization that works in this setting. And also, you may hope that larger settings can be reduced to this setting in some way. So clever abstractions could give finite MVPs. And here you can derive algorithms, you can derive results that demonstrate fundamental trade-offs and fundamental limitations for any algorithm. So that's also interesting. All right, so there are some questions. Can Gaumont try the same mechanism as warm-up? I'm not sure I understand that. So if you want Hong Chia Chen to rephrase that question, please do that. Another question, is there a middle ground between finite horizon and infinite horizon? I told you everything that I kind of know about this. So maybe the discounted setting is somewhere in between, one could say. Right. So back to our problems. So we want to design algorithms that give us good policies, given a finite MDP. And here we have to realize that this problem is not yet well defined, because we have to define in what format we're gonna get the data, which is the specification of what is the MDP that the algorithm needs to work on. And so here we can think about multiple different options. So one of the options is that the MDP is specified with tables. So that's where the tabular name also comes from. So the input to the algorithm is going to be the transition probabilities, the rewards, and these are just like big tables or matrices, and a desired suboptimality level. And the specification in terms of like a pseudocode in this case could be given as follows. You need to write a function with this signature. It takes as inputs PR and delta. And all right, so ignore this first line, that shouldn't be there. And the algorithm can do whatever with these tables. And at the end, it has to return another table, which for every state declares what action to take. So that policy would be a specific policy. It doesn't define a distribution. It defines only like which action to take. It's a deterministic state feedback policy or memoryless policy. But from the theory, we know that you can always find policies of this form, which are good policies. So there is no loss in generality by demanding that the algorithm returns a policy of this form. And the policy has to be such that its value function is, so the values that the policy delivers are data close to optimum. So that's captured here. So this is an inequality that compares, I view functions as vectors as well. So you can imagine that if you have a function from S to R, then you can imagine that, okay, this takes as input S, returns the value. Or you can also imagine that for every S, it gives you a value. You can collect this, and that gives you a vector, right? So that's an S-dimensional vector. So to me, functions and vectors are the same, and then you can compare vectors component-wise or functions component-wise. And so that's what's happening here. So this inequality means that for every state, the value that pi delivers, this policy that return delivers, is data close to optimum. So that's the first setting. And we call this the offline planning setting with table-based input. So another setting is also offline planning, but the input, the MVP, is given with a simulator that the algorithm can call. And so here you see what type of calls are possible with this simulator. You can ask for the problem size, and the simulator returns you how many states and actions are going to be in the problem. And you can also ask the simulator to generate a next state and a reward given a state and an action. So in this case, the S prime is going to be generated from PSA, and R prime is going to be, if this simulator is implementing this MDP that is given by PNR, then R prime is equal to RSA. So that's the requirement for the simulator. But the job otherwise is pretty much the same, except that we have a second input parameter as well, the xi, and the xi just says like with what confidence the algorithm needs to return a near optimal policy, the data optimal policy. And it is necessary because the simulator returns random information, and the output the algorithm building on random quantities, the output of the algorithm is also going to be random. So therefore, we cannot say that like for certainty, like if the simulator happens to return, with low probability, not representative samples, then you cannot demand that the algorithm is doing well. You can only demand that the algorithm is doing well with high probability. So that's the requirement then. So these are the two basic settings for offline planning. And then you can also think about online planning, which is a slightly different setting, in which case you won't implement a function called getPolicy. You would implement a function getAction. And that function takes previously a simulator as a parameter, and it also takes a parameter as state. And for that state, it has to compute an action. In the meanwhile, it can access the simulator in the same way as before. So this is shown here. So a state comes in, and then our little planner is going to access the simulator and maybe does it multiple times. At the end of the day, it returns an action. And if you think about it, if you keep calling this function, this implicitly defines a policy that you could execute interconnected with the MDP that is being simulated. And so this function itself, the policy is basically a specification of what action to take given a state. So here, this is specified using some code once we implement this function. And so then the requirement is going to be, okay, we have to specify this function getAction in such a way that the resulting policy is again, let's say with high probability, I think xi is warranted here as well, with high probability near optima, delta optima. All right, so these are the different settings that we can talk about. And the final setting is going to be where the simulator, it's a little change. Now the simulator only has local access. You have local access to the simulator. So previously, we could feed the simulator with any state and action that we wanted. But here, we can only feed the simulator with the states that we have previously seen. So this is called a local access simulator. Because sometimes you can just enumerate the states if you're thinking about Atari games or robotics. If you would think about like, oh, this state, is it possible like this memory layout in Atari games? Maybe that's an invalid state. So you can't do that. There you only have a local access simulator where if the simulator accessed some state, then you can refer back to that and then you can just say, oh, give me another next state from that state that we have accessed previously. All right, so we have all these settings. Regarding the computation model, I want to use the real RAM model. So not worried about, like, for example, how many bits does it take to describe tables or numbers. So this just means that arithmetic calculations take a unit time or unit cost. So their cost is just like O1, regardless of how many bits you would need to describe the algorithm. And this is like a common computation model that is used in all numerical fields, basically. All right, so that's nothing special there. So now finally we get to the very first algorithm. This is called policy iteration. And basically, this is the getPolicy function. This is an implementation for the getPolicy function, where the getPolicy function takes this table-based input, the P and the R, okay? And so this policy iteration works as follows. You start with an arbitrary policy. You start a counter, so your counter is going to be K. You initialize it at 0. Well, we store this constant, which is what we talked about. This is kind of like the effective horizon. And look, so there is this truncation check, like whether gamma to the power of K times H is bigger than that or not. And as long as this holds, we go into this loop. So this is going to, this loop is going to last. Basically, you have to solve for the k. The k is going to be, I don't know, like log, I don't know, age over delta, right? These many iterations, right? So the maximum number of iterations is going to be about this, right? After you invert. And so inside the loop, so this works really fast, right? Like if data is not too big, then this stops really fast. And the way it works is that we already talked about this loop ahead calculation, but here what you see is that instead of the optimal value function, we have the value function of the current policy. So what is hidden here is that we need to also calculate this value function in order to be able to perform this calculation. Otherwise, this is a totally well-defined finite calculation. You just have to calculate this inner product and sum these things up, compute the maximum, do this for every state. So what is this value function? So the value function was defined, and it turns out, if you think about it a little bit, it's not hard to see that the value function satisfies a fixed point equation. And it satisfies the equation that the value function is nothing but the reward. So you can create this reward vector, which for a deterministic policy would just at state as assign the reward of that the policy would achieve, the immediate reward that the policy would achieve at that state. So that creates a reward vector. And then you can also create a transition probability matrix, which by indexing it with S and S prime, S is the current state, S prime is the next state. So this is a row index, and this is S is a row index, S prime is a column index. So this would be just P at S and pi S. Again, like policy is choosing this action, and then we have to look at what is the probability of given that arriving at state S prime. So these are fairly obvious definitions. And so you get this matrix, you get this vector, and the value function turns out to solve this fixed point equation. It's called a fixed point equation because on both sides, you see the value function. And so the logic of this is that what is the value at a given state for this policy? Well, it's going to be the immediate reward that we get, and gamma times the future reward that we get. But if once you get to a new state, what is the value there? Well, the value function gives you the value there. So that's why you get the value function on the right-hand side as well. Because by definition, the future looks the same as the present. And so this on its own is a linear equation for V of pi. So this is a vector, this is a matrix, so you can rearrange and you can solve, and V of pi is equal to I minus gamma P of pi inverse R pi. So that's the calculation that needs to be done in order to be able to obtain the value function. So it's a matrix inversion, effectively, which can be done in less than S cubed time if there are S states. So once this is done, so that's the next policy, and this is called the greedy policy with respect to this value function. This is greedification. Greedy is good if the value functions that you're plugging in here, like this V of pi is correctly chosen. If it was V star, this would give you the optimal policy. If it's V pi, it gives you a policy which is known to be strictly better than the previous policy. So that's actually a theorem, and one can prove that. So anyhow, so after this calculation is done, the current policy is replaced with the new policy, the counter is incremented, and we are checking the whether the termination condition of the while loop is met, and if it's met, then we're returning the policy. All right, so Maximin and TSN is asking whether the inequality in the second get policy should hold with high probability uniformly over all states. Good question. So this is the second get policy. Right, yeah, absolutely. It's uniform over all states. That's right. All right. So that's policy iteration, and the shorthand that I'd like to introduce is that for this calculation. So obtaining pi prime by feeding a value function to this argmax. So I want to introduce the shorthand that you just apply this function gamma to v of pi and returns this policy. Oh, yeah, okay. So Maximin also asked whether it would make it simpler to demand it only for some states. Well, we kind of, yeah, you could consider such things. And that's also fine. It's kind of like localized notions of these requirements. That's fine. It doesn't change too much though. Because that state that you demand this to hold, maybe it accesses all the other states, and you have to know how to act at all other states to be able to know how to act at a given state. So it's kind of like this localization doesn't buy too much. So the next algorithm that I want to talk about is called value iteration. Superficially, it looks similar to the previous algorithm, except that here there are no policies computed, only functions that are mapping states to reals. So that's why it's called value iteration, because these are called value functions. The idea is to approximate V star. So V star was the optimal value function, and we know that if we take a greedy policy with respect to V star, that gives you optimal policies. So this is an optimal policy. So the idea is to try to calculate V star, and this calculation is very similar to the previous one. You just take the maximum value of the immediate reward plus gamma times the future value at the current estimate of V star. That's your V. You initialize this, let's say, at 0. And you just do this for every state, and then you update, replace the value function with the new estimate, and then at the end, when the termination condition, which is identical to the previous one, is met, and the continuation condition is not met, then we're just returning the policy that is greedy with respect to the value function that is computed. So V is called a value function, even though it is not really a value function of any policy. It is just a function that assigns values to states. All right. So why does all this work? So the reason all this works is because of Banach's fixed point theorem, which says that if we have a contraction mapping, so the contraction is simply a map that takes to any two inputs which live in a normed complete vector space. So these are U and V, and the map maps them to some other vectors, TU and TV. And if you calculate the distance between TU and TV, distance given by the norm, then you get something that's gamma times the original distance between u and v. So these distances between u and v are shrinking by a factor of gamma. So this is called a contraction. And generally what you should imagine is that if you continue doing this, then, well, everything is kind of like pulled towards a point. This is only possible if everything is pulled towards a point, and that's the fixed point of the contraction map. And Banach's fixed point theorem actually just says this. For any contraction map, if you start to iterate the map, so t to the power of n just means that you're applying t, this function, n times on the top of its input. Then as n goes to infinity, this is going to go to a unique vector, a vector, which is the fixed point of t. So it satisfies this equation. And here the completeness of the vector space, for Euclidean space, it just holds whatever norm you choose. But completeness just means that if you take any sequence, which is a Cauchy sequence, which means that kind of like the oscillations in the sequence are decreasing in the nature. So you take an infinite sequence of such Cauchy sequence, then it has a limit in the space. So then it turns out that the maps that we have seen, so T pi is, so here there is this shorthand that I forgot to mention. So the shorthand just stands for this calculation. So V prime is calculated from V with this loop. So the shorthand for that is that you take this function t, you apply to v, it returns the new function. This function, because it acts on functions, it's sometimes called operator. But it's really just a function. And so the other map was T of pi. So that's written here. So the right-hand side here. So this is the definition of T of pi. So T of pi v is just r pi plus gamma times p of pi v. That's the definition for T of pi. And v of pi is a fixed point of T of pi. And so it turns out that these are gamma contractions, and that's just simple algebra. And then you can apply Banach's fixed point theorem. And it says that T pi has a unique fixed point, and this T operator also has a unique fixed point. This operator is called the Bellman optimality operator. Its optimality is because there's a max there. And the other operator, the only difference is that instead of choosing the best action, the action that maximizes this quantity, you choose the action that is specified by the policy. So that's T of pi, and that's the policy of variation operator. So these are contractions. And then the fundamental theorem, which I mentioned before, says that for any finite MDPs, the following hold. Any policy that is greedy with respect to the optimal value function is optimal, and V star is a fixed point of the Bellman optimality operator. And here I wrote the proof sketch, but in the interest of time, I will not go through this. I'm happy to answer questions if the proof sketch is more or less complete. It's a complete proof. So if something is unclear, I'm happy to answer questions related to this proof sketch later, Facebook or whatever chat. So that's the fundamental theorem. And why is this important? Well, it shows the structure of the MDPs. That's why I call it the fundamental theorem. And it shows that it's enough to calculate the optimal value function if you want to know how to act well in an MDP. And so all the algorithms, so here's some clarification about terminology. So people often talk about dynamic programming. So my understanding of what dynamic programming is that any algorithm that tries to reason about what policy to use by reasoning through value functions is a dynamic programming algorithm. So that's dynamic programming. Reasoning about pi star through V star or approximations of V star. And here you can think back about shortest path calculations using Dijkstra and whatnot. A lot of the basic computer science algorithms for graphs and paths and flows, they, in a nutshell, dynamic programming in this sense, they do the same thing. They calculate values. They assign, cost to go to the nodes, and so on and so forth. There is a very strong parallel to those algorithms and to those ideas, and what we're doing here with MTPs. All right, so I talked about these two algorithms, and then the question is, what do we know about these algorithms? Why do we keep talking about these algorithms? Are these algorithms any good? And perhaps surprisingly, well, there were some very odd results about policy iteration and value iteration, like kind of folklore results. But until very recently, policy iteration was not super well understood. So Yinyu Ye and Bruno Scher, among others, contributed really fundamentally very recently to this understanding of policy iteration. And so here comes two results, which are kind of neat. So for policy iteration, we know that the number of operations that are sufficient to produce a data optimal policy, it kind of looks like this. So this quantity has a bunch of terms in it. So there is the effective horizon, the 1 over 1 minus gamma that tends to show up. It's like if you want to think about discounted problems of like approximations to discounted problems using finite horizon problems, this is the number of steps that you should be kind of thinking about in a finite horizon approximation to the discounted problems. And so this multiplies a term. So if gamma goes to, or before that, if gamma goes to 1, then this blows up. So that this becomes really large. So large horizon problems give a hard time for both policy iteration and value iteration because the running time scales linearly, at least according to an upper bound. And I'm guessing that you can produce it's not too much work, lower bounds that would also show this behavior. So large horizon is difficult potentially for these algorithms. And the second term for policy iteration is an interesting term in this, it is in this bracket. So here, okay, so this notation here, this N notation, so that's shown here in the bottom. So A and B is just a shorthand for writing the minimum. It looks better. It's like a binary operation instead of just this function notation for the minimum. And so this takes the minimum of the number of state action pairs. So that's SA. And this other quantity, which we have seen, it's kind of like the iteration number, the number of iterations that policy iteration needs to make, except that there is this blow up by age. And so here, and after this, the last term in this bracket is the cost that a single iteration takes in policy iteration, because you have to calculate the matrix. You have to calculate the matrix. Is that the matrix calculation? No, that's like the gridification. So for every state and every action, you have to calculate some value. So that takes SA time. And then you take the best action. Here you have to calculate the P of pi matrix. And here you have to invert maybe the I minus gamma P of pi matrix. And of course, this term is dominating this term. So altogether, so this is kind of the structure of how policy iteration works. And for value iteration, you see something really similar, except that here you have S squared A. And here, if we are counting, for example, the parts of S, then we have something higher. So from these two terms, we would have S to the power of 3.373 A. It's interesting that the cost of matrix inversion is not even known whether it can be done in S squared times. But even if that would be possible, then this would be cubic at least. So it's definite. If we think that this is the best possible way to implement policy iteration and these bounds are tight, then policy iteration seems to be faring worse than value iteration when the number of states is large. On the other hand, value iteration has this term only, and policy iteration has the minimum of these two terms. So what does this tell us? So if I take delta, the required suboptimality level, go to 0, then what I see is that this log 1 over delta blows up with delta going to 0. So log 1 over delta is going to go to infinity. And this is going to impact the compute time of value iteration. And there is actually a paper that shows that this term cannot be removed. So value iterations, computation time, delta optimal policies can really blow up. Whereas for policy iteration, what we see is that there is limiting a limit on how much computation we're gonna need, even if the precision becomes really, really high. The demand for precision becomes really high, because here we're taking the minimum of the number of state action pairs and this log 1 over delta quantity. So if this becomes really large, SA takes over. So altogether, when delta goes to 0, then policy iteration wins over value iteration. And if S goes to infinity, then value iteration is winning over policy iteration. So it's kind of interesting that we see these trade-offs from these theoretical results. And I believe these trade-offs are actually real. But okay, so lo and behold, this was just a algorithm-oriented analysis because we took two specific algorithms and we tried to understand which instances are better suited for each algorithm. So we can also think about a problem-oriented analysis when we can ask the question, okay, but like, what is the best possible runtime for algorithms? For that, again, we have to be specific about the setting. So one of the settings is, for example, when the MDP is given with a table and we want the offline planning to solve the offline planning problem. And there it's not hard to figure out that any algorithm is going to need at least S squared A steps on some MDPs. And so some illustration is shown here, but maybe the next slide is a little bit better. So if you have altogether S states, you split the S states into 3 different groups. They're the ground states where you have to make a decision about which action to choose. So these are the ones, the interesting states, where deciding which action to take is going to be difficult, because one of the actions is going to be such that it takes you to this group of states, so to some state in this group, and I call this the heaven states. The reason being is because once you get to a state here, no matter what action you take, you get the reward of 1 and you stay at the same state. So the value that you get from being in this state is 1 over 1 minus gamma. And all the other actions, if you take any other action, then they take you a Hall state. And in a Hall state, there is no reward. So the value that is assigned to the optimal value that is assigned to Hall states is 0. So the optimal value that is assigned to heaven states is 1 over 1 minus gamma. So and the value here, because there is a discounting for this state, is of course gamma over 1 minus gamma. You should always take the action that takes you heaven. But if the MDP is given with a table, how are we going to figure out which action to take? Which action is the one that takes us to heaven? We have to look at all the state action pairs, basically. So that's kind of shown in this table. So let's say the ground states are state 1 and state 2. And these are then in one of the boxes, there is a reward, but before opening pretty much all the boxes, you have no idea about what the reward is. So in such a situation, every algorithm needs to do all the work. So this is a hard case for any algorithm. Any algorithm will need to basically read as many states as, so there are S over 3 states here and S over 3 states. So it has to read basically S over 3 states, and there are S over 3 states here as well. So that's like S squared over 9 times A. So sorry, there is an A multiplier here. So it has to read every entry. All right, so that's kind of the needle in a haystack argument that we often use to prove algorithm independent lower bound. So the interesting thing here is that this lower bound that says that that this is the amount of work that needs to be done is independent of what algorithm we choose. It applies to any algorithm, but it's not nothing really that surprising. It's like just really this argument that if you have so many boxes, one of the boxes has a price in it, then you basically have to open all the prices if you want to figure out where the price is. All right. So now an interesting thing. So if we change the setting and we think about as an MDP given by a simulator. So global planning still, but the MDP is given by a random access simulator. Then it turns out that you can design algorithms whose runtime is not dependent in a quadratic manner on the number of states. So you can reduce the runtime to be linear to the number of states. And that's basically because over the next states, you only have to kind of calculate averages. And for that, you don't need too many samples if you're using a simulator. So averages concentrate really fast, regardless of the cardinality of the set that you're taking the values from, over which you're taking the average. So the cardinality there is not really expected to appear. And lo and behold, with this representation, MDP representation, you can reduce the complexity, at least the query complexity of like how many readings simulator calls an algorithm needs, from quadratic dependence on the number of states to linear dependence. So you can also see that there is a 1 over delta square dependence here, and this is both a lower bound and an upper bound, and so that's interesting. So this, if we're thinking about this as a lower bound, so it has 2 parts. There is this SA part. Okay, it has 3 parts. There is the SA part, and there is somehow the H cube part, and there is the delta squared part. The SA part is really just a needle in a haystack situation. The 1 over delta squared part is about the statistical uncertainty that you get if you're using a simulator, because it returns random things. And if you want to know whether a coin is biased, and the bias could be as large as data, but maybe just data, then you need at least 1 over data squared coin flips to be able to decide whether the bias was smaller or larger than data. So that's coin flips, and that's statistical uncertainty, and that's why in a lot of the bounds you see this 1 over data squared, and this 1 over data squared cannot be reduced. It is just like how fast uncertainty decays. From the central limit theorem, you have also seen that the standard deviations decays with like 1 over root number of samples. So 1 over root n behavior that like translates to this 1 over data squared, because you just solve like 1 over root n smaller than equals to data, and then you invert, and then okay. So how many samples do I need? Well, at least 1 over data squared. And so the third thing is this h cube, and the h cube is illustrated by this little figure here. So the h cube comes from the sensitivity of the values to variations of the parameters. And so here the optimals in this little MDP, there are 2 states. In state number 1, you stay with probability P, and with probability 1 minus P, you move to state number 2, and that state number 2, you always stay there, and you receive no reward. Whereas when you're making this transition from state 1, you always receive a reward. And the value of state 1 is a function of P. And if you calculate how sensitive the value to the function of P is in the discounted problem, you will see h cube popping up, essentially. Yeah, fundamentally, that's the reason h cube is there. Okay, so Chuin Hangyo is asking whether in the haystack example, there's an assumption that each stack examined is independent to each other. Well, I would say that are there correlated haystacks in real cases? If yes, can we address them in the same way? Well, when we apply this haystack technique, we make sure that everything is independent. So that's the answer. So you kind of like get to the heart of the problem by discovering how many haystacks you have and how many haste you have there, or like how many boxes you have. All right, so this is a sensitivity, this is statistical uncertainty, and this is needle in a haystack. All right, so another result of this type is local planning, but you have a local access simulator. So in this case, so in the previous case, we had SAH cube over data squared. Everything is polynomial, but there is this linear dependence on the number of states. So in this case, you can build a tree, a lookup tree of depth h, roughly, and with setting the number of next states and using randomly many, you use the simulator to generate this tree, because for each of the node in a tree, for each of the actions, a node represents a state. For each of the actions there, you generate a certain number of next states using the simulator, and then you branch, do it for 8 steps, and then you're calculating values backwards as if that was the full MDP. And if you do this, then you can prove this upper bound on how many samples you need to read out a data optimal policy. And the nice thing is that this is independent of S. So the good thing is that in local planning, where you just have to implement this get action function, you don't have to return a policy. The haystack, one haystack that came from that you have to look at all state action pairs, because, well, we have to report what action to take at every state. Well, it's unnecessary, right? Like if you can run a planner in real time in this online planning fashion. So I was calling this online planning. This should be called online planning. Then this is unnecessary. And then you can completely eliminate the dependence on the number of states. The problem is that you see an exponential dependence on age, the effective horizon. And so the problem there is that age is also typically pretty large. And so we kind of traded off large state space to large horizon, and like, unfortunately, in problems we are interested in, both of them tend to be large. But here there is also a lower bound that says that no algorithm can do better in this setting than a to the age if the number of states can be arbitrarily large. Okay, so that's the nature of the lower bound. So here there is no limit on the number of states. So the algorithms need to build basically this tree, and in the lower bound you actually construct a big tree, and the algorithm needs to look at all the leaf nodes. It's just a deterministic transitions. Algorithms have to look at all the leaf nodes. If they don't look, then they may lose. All right. So again, important thing, this was problem-oriented analysis. So we were looking at different problem settings and the problem classes, and we figure out what is some complexity measure, resource need use, resource use needs for these problem settings. All right, so what did we learn so far? Value iteration and policy iteration have complementary strengths. Sampling can help reduce complexity. And so far, we have seen that all algorithms suffer from one of the following curses, either exponential in the effective horizon complexity or linear complexity. It's a function of the number of state action pairs. So the problem is that, of course, we're interested in the case when the smallest of the number of state action pairs and the horizon is also large. And so we cannot afford to see these in the bounds. So this is the problem. But I'm gonna postpone this problem a little bit because I want to talk about an important aspect of reinforcement learning before getting into this, discussing what other options when we are in this large scale setting. And this setting is the online learning setting, but maybe we should hit pause here and give people some time to catch up and maybe type some questions. So how about we take like a water break, restroom break, whatever of 4 minutes. We'll be back at 8:40. I mean, like, I'm gonna be here. And so if you have questions, then this is, I think, a good time to ask those questions for the previous part, because now we're gonna go into this online learning setting, and after that, we look at the functional approximation case. Okay. So, I don't know what the time is there. So here, I'm talking about 8:40 p.m. So it's, I think that this is the part that's important. Okay. So then for 10:40, that's right. And it's AM, of course. I didn't want to make a mistake. right? So geometric series. Oh, okay. So then the question is, why is H this? As I said, a lot of times, so this contraction arguments appear in these proofs. So if we take contraction operator and we start to iterate on some function u, and we compare this to the fixed point of the operator, then, well, this is the fixed point. So this is also equal to t applied n times to v star. And how many times you're applying t, that's how many times you are shrinking the distance between the inputs to the function or the operator by a factor of gamma. So every time by a multiplicative factor of gamma, so altogether that shrinks the distance by a factor of gamma to the power of n. And so usually there is some absolute value, like how big are these functions. And by the way, because of this relationship, so this is equal to h, so these functions are individually between 0 and h. And so if you have this box, which is the hypercube of size h, and you have two elements in this hypercube, and you compute the max distance between arbitrary functions, then this max distance, the largest possible distance that you can get is also h. So then you get that after you apply the contraction operator n times to this arbitrary initialization, 0 or whatever, you are very close to the fixed point. Your gamma to the power of n times h close to the fixed point. And then you can solve that, okay, like if I want to be, I don't know, epsilon close, then you can reorder this, and then you see that like, okay, this is how big oops. There is no eraser. So n is greater than or equal to log h over epsilon divided by log 1 over gamma, and 1 over gamma up to very good approximation is equal to 1 over 1 minus gamma. So this is a very good approximation. As gamma goes to 1, the difference between these two guys goes to 0. So this is of this size, which is equal to h times log h over epsilon. So this is the calculation that is at the heart of all of these arguments, and that's why you see the dependence on h showing now. All right, let's start. So online learning. So here the important lesson that I want to convey is that not all exploration strategies are born equal. And other general lessons is exploration is separate from optimization, but I will also argue that everything is just optimization. And if you want adaptive algorithms, and we'll be specific about what that means, then optimism is the answer, and I explain what optimism is. and other simple strategies like epsilon greedy, falling short. And another lesson is going to be about regret. Like in online learning, people oftentimes talk about regret, and there's a good reason for that, and I talk about that. So what is the problem setting? So the problem setting is very similar to the previous one that we have seen. You just have to implement this function getAction, which has a which has three inputs. S, that's the current state where you should compute an action. So it's like the online setting, right? And the other two arguments are just the number of states and number of actions. And a special case which comes up all the time is the bandit setting. So in bandit problems, simply put, these are kind of MDPs where you have only a single state. So there is, okay, maybe the number of actions that should be part of the initialization or whatnot. But the number of states and which state you are at there, that's superfluous to ask. So what performance metric to use? That's the first question. If we want to design an algorithm, how should we measure how good is this algorithm? So as opposed to the previous slides where I had the problem settings, where I had the problem specification like fully there, like what do we want from this algorithm? What is a good getAction implementation? Here we didn't have a specification, so let's talk about it. So the obvious quantity would be, let's say, the total expected reward for a given time horizon. If I keep calling this getAction and then make a move with the environment, with the MDP, then call the getAction on the new states, and so on and so forth, I get a sequence of state action pairs. I can sum up the rewards along it. There is no discounting in this case. It's just like the total reward. I want to maximize it for the lifespan of this agent. Okay, so this is undiscounted total reward maximization. The new thing here is that there was no other way of seeing things than by interacting with the environment. And that's where this specification falls a little bit short, because it's kind of like, it should be, somehow we should get feedback about what the rewards are. So maybe here there is a reward as well, because there is this getAction being called, and it sends an action to the MDP, and the MDP reacts with the next state and the reward, which is the next input. So the only way you learn about the MDP is by interacting with it. There is no separate simulator, and every action counts. Like if you choose an action, then it incurs a reward, and if you chose an action which doesn't incur a lot of reward, then you may regret that. All right, so maybe the goal should be to find a single algorithm that achieves as much reward as possible, no matter what the MDP is, that the algorithm is interacting with. So say we have this class of MDPs, let's take M to be the class of MDPs, where we have S states, A actions, and the rewards are in 0, 1, to be specific. So then maybe a good algorithm would be one that solves this max-min problem, right? So if I choose an algorithm, A, then a mean adversary may choose an MDP, and I get the total expected reward on the MDP on which my algorithm works the worst. So A, this should be A, the same A as goes in here. All right, sorry, that's calligraphic A. So does this make sense to use this performance metric? Why or why not? it turns out that this actually doesn't make any sense. Because if I take any algorithm, I fix any algorithm, if I take an MDP, but the reward is identically 0 for all the actions, and then that was a load, that was within a class, then the worst case is going to be exactly this MDP for that algorithm. And it didn't matter which algorithm I chose, right? So for all the algorithms, it happens that the worst case total value that I can get is 0. And we want to maximize this. Well, for all algorithms, it looks 0, so we can choose any algorithm. So this is a vacuous metric. It's a bad metric. It's uninteresting. And the worst case is also uninteresting. So how do we save this? So we have to listen to two gentlemen who are shown here, Abraham Wald and Svaj, I forget the first name. But anyway, so their algorithm was, or their idea was that the metric should express how much an algorithm loses compared to the best specialized algorithm. And that defines regret. So regret is how much we are regretting of not using the best algorithm specialized to an instance. So the regret of an algorithm A on an instance MDP instance M is going to be how much compared to the best possible algorithm, which would know about this instance. So it would just like use the optimal policy all the time. How much are we losing compared to this? So obviously this is going to be a non-negative value because this is a specific algorithm. It cannot get more values than the best algorithm. So we can only lose. So it looks a little bit pessimistic. But at least for the uninteresting MDP, where the reward was identically 0, the problem goes away, right? Because for the uninteresting algorithm, my algorithm gets, whatever algorithm I choose, gets 0. Any other algorithm gets 0. So the regret on this instance is 0. This is the easiest instance ever. So they can flip things around and put things into place, right? Like, no, everything falls into place. Like, it should be easy. This instance should be considered as an easy instance from an algorithm design perspective because there is nothing much to be gained by being clever about what algorithm to choose, right? So that's the idea, that we should use regret. And then, okay, similarly to the previous ones, we have this multi-objective optimization problem over all possible instances. Just look at the worst case. So what happens with my algorithm if I choose the instance which maximizes the regret? So regret is negative value, right? So there is this negative sign here. So we want to minimize regret. We don't want to regret of choosing an algorithm, right? So that flips around the maximum mean. So we want to choose the algorithm that minimizes the worst case regret, all right? So again, algorithm design is multi-objective optimization, and to convince you that it is really a multi-objective optimization problem, just recall this recent and very well-known paper by Vlad Mich and other colleagues from DeepMind, Human Level Control through Deep Reinforcement Learning, which appeared in Nature. They are showing results across many different instances. So here, these are instances in our language. And you have different algorithms compared. So in this figure, you have DQN and a best linear learner. And you want to choose the algorithm which is the best in all possible instances. Well, you can compare the algorithms based on their worst performance. So that's like what the Minimax would choose. But you could also try to find out other ways of comparing algorithms. But this is one way. So, and it's a sensible way, sensible first approximation of how you should be doing multi-objective optimization. All right. So unfortunately, this still doesn't work. So the minimax regret turns out to be infinite. Oops, why is that? Well, this is a delicate issue. The issue is that if you have, this doesn't make sense. Okay, so RT over T, the limits of RT over T star is infinite. So that's kind of the problem. Well, yeah. And we don't like that. So the average regret per time step is infinite, even if we choose the best algorithm, for best worst case algorithm. And the reason for that is that in these MDPs you have the state space, and there could be states which are really far away from each other that take a lot of time to travel between, even with the fastest possible way. And if a learning algorithm needs to compete with the best strategy, then it needs to check out basically the whole state space. But since this quantity, the diameter of an MDP, is unbounded, it depends on the transition probabilities. So the transitions can be such that like you take a lot of time to move just between two states because you mostly stay with very, very high probability. You stay in place, right? Then it takes a lot of time, and you can make this very, very slow, this travel time. And if you make it very slow, then it will be very slow to learn about these MDPs, and then your regret is going to suffer because of this. So therefore, what we are doing is that we're going to limit the instances to those instances where the so-called diameter is small. So instead of considering all possible MDP instances, we only consider MDP instances where the diameter of the MDP is small, where the diameter is the worst travel time between two states. So this d pi m is the expected number of time steps that takes by policy pi in MDP m to get from state S to S prime. And so that's the quickest way of getting there. So for every step, you pay a cost, and total cost should be minimized. And the diameter could itself be infinite. So if you have an MDP, which has, like 2 parts, and you can't even go from here to there, so they're disconnected, then the diameter would be infinite, for example. Okay. It can also happen that there is a state that connects these two. So you start here, and then you transition here or there with some probabilities, maybe 0.5. And after that, you cannot go in between these 2 parts of the MDP. The diameter is infinite, and regret doesn't make sense in that case. So you have to do something else with the MDPs in which the diameter is large, because, well, maybe in this state you had one action and you try this action, then this happens, and if you try some other action, it always goes there, and this is heaven, and this is hell, and you didn't know initially because you're a learner whether you should choose this action or not, and so things don't work out. You have to limit the class of MDPs further, and one way of doing that is just by saying that, well, you should be able to go from any state to any other state in the MDP, because otherwise it is not possible to learn about the full state base, because there could be these traps in the MDP and you cannot escape the traps, and therefore learning is just like becomes a mess. So that's what people do. So we restrict the class of MDPs to this class where the diameter is finite. And then you can prove the following result. There exist 2 constants such that for any big enough t, So if T is bigger than diameter times number of state action pairs, and the diameter is big enough, then, by the way, the diameter is pretty much always this big, and the number of states and actions is big enough, then it always holds that the regret, the minimax regret, is between these two quantities. So here, the two quantities almost look identical. So the square root AT behavior is the same. And the square root T is something that should be familiar. If we divide by T, all the size, then this becomes 1 over square root T. And we already talked about that 1 over square root N or 1 over square root T. So that's like T is the number of interactions here. That's kind of like the statistical uncertainty. So here, what we see is that the average regret per minimax regret per time step scales with 1 over root T, which expresses the statistical uncertainty. So that comes from this coin flip property. You cannot reduce this any further. So that's what the lower bound says. The SA part here in the lower bound is coming from a needle in a haystack argument, essentially. The D part comes because in order to just see all the states, you have to pay D times D actually. For every state, you have to pay kind of D. So that's the reason you see D there. And what you see also is that in the upper bound, DS is outside of the square root, versus in the lower bound, it's inside the square root. I think that most people believe that it should be inside, but currently this gap is still open. So this is how we read the result. So what next? So what should we work on? So that's kind of like theoretician's dilemma. If you see a result like this, should we remove the log factor? Should we close the square root DS gap? Well, yeah, we can. These are all reasonable, meaningful problems. And what I wanted to say is that they often push us to think about the problem deeper and then discover new properties and then potentially discover new algorithms. So for example, in this case, if you believe that the upper bound should be lowered, that means that we need a new algorithm. But before we go there, new algorithm, what is the algorithm? How do we establish this result? For the lower bound, you can hopefully imagine that you can use this needle in a haystack argument and then some modification to it and the statistical uncertainty argument to get the lower bound. For the upper bound, we need an algorithm. Most of the time, the way we establish upper bounds is that we show that there exists an algorithm for which the regret is not bigger than the desired quantity. So again, like this was problem-oriented analysis. So what is this algorithm? So it's an interesting algorithm. It's called UCRL2. And the authors are Jaksch, Ortner, and Auer. Jacob Jaksch, Ronald Ortner, and Peter Auer. And so the algorithm is a model-based algorithm. It builds an empirical model. And the empirical model building is shown here. So basically, the algorithm collects all the samples, estimates transition probabilities with empirical means. So TTSA, just like how many times you have seen a given state action pair. This is just an indicator function, which returns 1 when the condition in the argument is true and otherwise returns 0. So this just counts how many times we have seen state action pair in the data. The data is this SU, AU, and also the reward. I guess like, okay, so here, for simplicity, we assume that the reward is known. And all that we don't know is the transition properties. It is usually the trouble is learning the transition probabilities, and not knowing the transition probabilities is more expensive than not knowing the rewards. Extending the algorithm to the case when the reward is known, unknown is easy. So the reward function is known, so that's why we don't have to estimate it. Estimating transition probability is just done by these empirical counts. So how many times we transition to state S prime versus how many times we have seen the given state action pair from which we're transitioning to S prime, divided to that gives you the empirical estimates of the transition probabilities. And then once you have the empirical estimate of transition probabilities, what this algorithm does and what's new here is that instead of saying that, well, okay, let's just like maybe solve for the best policy given this and the rewards, which would be a model-based solution algorithm. Instead of doing that, it says that, well, we don't quite know what these transition probabilities are. So we can create these confidence sets that collect all possible transition probabilities. So all of these are possible, where the, let's say the L1 distance between the next state distribution and the given distribution, so this is for a fixed SA, is not much larger than how many times we have seen under the square root the number of state action pairs. And there are some log factors here for mathematical precisions, those are included. Those are actually pretty important to prove that this algorithm works, and like to make actually the algorithm works. If you try to just drop it and then replace it with a constant, that you can prove that this algorithm is not going to work very well. There is also the number of states appearing there under the root. And well, this, long story short, this confidence set at a given state action pair is chosen in such a way that with probability 1 minus delta, during the execution of the algorithm, the true transition probabilities always belong to this set. So the way I imagine is that for every SA, we have a simplex, and within the simplex, there is p hat. So that's p hat for a given SA. That's a point in a simplex. And then there is this confidence set, and this confidence set is chosen in such a way that the true transition probability is also always included in this confidence set. And then the algorithm goes and says that, well, if you don't know which of the models that you can compile this way is the true model, so we should consider all of them. And when we're considering all of them, which one shall we choose? And here the algorithm is pretty clever. It says that we should choose the one that gives the best word. Bet on the best. So this is what some other people gave this is the name that some other people gave to this idea, bet on the best word. So all these transition probabilities are possible. So for every state action pair, we are free to choose one. Let's compile them in such a way that the average reward, if we read out like what the average reward is under all these transition probabilities chosen, is the largest possible. So that's given here. So for all the transition probabilities, we can get the average reward. And here, I didn't explain why we are switching to the average reward, but in the long run, this total reward and the average reward are kind of the same. So to maximize the total reward, the implicated criterion is really the and then we choose the best possible policy for that choice and the best possible initial state. And that gives you the average reward, and choose the corresponding policy And once this policy is chosen, so I'm just explaining it, this step here. So this is the optimal policy in their MDP, which is chosen using this better than the best or optimism principles. This is also called optimism, because we are optimistic about that the transition probabilities are going to be the ones that give the highest possible average reward. So we choose this policy, and then we follow this policy for a while. And for how long? We're going to follow this policy until for at least one state action pair, it happens that the number of times we see the state action pair at least doubled compared to how big this number one was, how big the number of visits to the state action pair was at the time when we chose the policy. So we wait until we collect kind of a significant amount of information, and then we switch to a new policy. The reason we do this is because otherwise it could be a bad situation where you have two states and you can travel between the two states, but if you travel between the two states, you get no reward. If you stay at any of the states, you get a reward. And then the optimistic algorithm, if you didn't have this slowing down effect, this choice, this while loop there, would just jump back and forth, always thinking that maybe from the other state it can get more reward. And along the way, it would never receive any reward. So this slowing down is necessary, and this is a simple way to do it. You can also understand that, like, it makes sense to not to switch to a new policy before we collected kind of sufficiently significant amount of new information. So that's kind of like a general principle as well. Why run and rush to compute something new when things didn't change at all? So before you see this doubling of the number of samples, at least for one of the state action pairs, there is really no reason to change a policy, because nothing would change too significantly. And we're not losing by this rare switching condition. And it also helps with computation, so it has other benefits as well. All right, so this is the algorithm, and this implements the optimism principle. And why does optimism work? Well, optimism works when if you try something, then you learn about how good that is. Because if you choose then in an optimistic fashion, and you were overly optimistic, then you're gonna learn about that, well, this was not a good choice. And this is the situation in reinforcement learning. If you choose something, then you might be learning about a lot of different policies, but definitely you're learning about the policy that you chose, right? And optimism is a good fit to this situation where you get some good evaluative feedback about the choice that you just made. In this case, the policy that we chose. All right. Lastly, how about simpler strategies? So do we need these complicated optimistic algorithms? It is a simple illustration that I want to use to argue that optimism has some unique benefits which are hard or impossible to achieve with other simple mechanisms. So one simple mechanism is called forced exploration. When you would explore, let's say, uniformly at random, choosing the actions in the MDP for a while, and then you learn an MDP, and then after that you switch to the so-called exploitation mode. When you're estimated the model, you compute the optimal policy with respect to the estimated model, and just like follow that policy until the end of, I don't know, your horizon. And so this is called forced exploration. And you can do forced exploration in many different ways, and many algorithms implement this. So epsilon greedy would be another algorithm that sort of like forcing exploration. So epsilon greedy, as you probably know, is the algorithm which does what I said before, estimates the MDP. And when it comes to choosing an action, it flips a coin. And with probability 1 minus epsilon, it follows the greedy policy that it computed with respect to the latest value function of the latest MDP estimate. And with probability epsilon, it chooses an action uniformly at random. So in epsilon greedy, it's kind of doing the same thing. It's like blindly kind of like trying to enrich the data and avoid some starvation. So yeah, here we should also mention that if you take away exploration at all, like you don't apply optimism, you don't apply exploration at all, this epsilon greedy, then it's really easy to create situations where you run into trouble. You can think about that you have two actions to try. It's a bandit problem. There is only a single state. There is stochastic reward. And maybe it's Bernoulli reward, and one of the actions has a high reward, high Bernoulli reward. The other has a low Bernoulli reward. And you try the action that should be the better action, but you're unlucky and you see a bunch of zeros initially. This happens with positive probability. So this basically happens all the time. And if you're just greedy, then like you never find out. And then once you see that, okay, this has just zero reward, you quickly switch to the other action that with high probability returns a 1. And so you just stay with that other action. And so this policy incurs a linear regret. So it doesn't even find an optimal policy in the limits. So this is a bad strategy. You need to add exploration. And so the forced exploration would be one simple way. But the problem is that there is this tuning parameter. So we're going back to this hyperparameter. It has this hyperparameter of like, how much exploration should I add? And you can try to tune it. And so this graph kind of shows for different problem instances. So these are problem instances characterized by some real value. So all the problem instances in this simple case can be on this line. So these are problem instances. And this is the expected regret for the different algorithms. And then here you see different choices of the hyperparameter M, which is like how many exploration steps you need. And across the different instances, you see the performance of the algorithms. So if you choose the hyperparameters, this is like how many exploration steps to do at the beginning to be low. Then you see that like here, the curve is really high. You want to minimize. So the regret, the lower values, so the better. You want to minimize it so that we don't like this part of the curve. And if you choose something opposite, like a big value, 100, then you see that like here, you are in real trouble. And even for any other value, the 50 and the 75, here you are in trouble. So the blue curve behaves nicely here. So we really should do what the blue curve is doing if the instance comes from this part. But we should really be doing what the red curve is doing, right? When we are in this part of the instance space. So it's like the hyperparameter needs to be chosen dependent on the instance. So that's like adaptivity, right? And so it turns out that optimism does this for you. So UCB is the name of the algorithm of the specialization of the user algorithm to bandits that I described. So in bandits, you only have one state, and then maybe the reward is stochastic, so you're uncertain about the rewards, but you're optimistic. You use this optimistic estimates, upper confidence bounds, so UCB stands for that. And you always choose the arm which has the higher upper confidence bound. So it turns out that if you plot the regret of UCB, it is pretty close to what you would get from this gray curve, which would be the theoretically optimal but infeasible choice for the hyperparameter of M. So this shows that if I knew the problem instance and I can choose the value of this hyperparameter based on the problem instance. What is the value that I could get? What is the regret? That's the gray curve. And you can see that the black curve follows it pretty closely. And so that's what you get from optimism. It's adaptivity to the instances. And then that's like a huge advantage. So we're back to this multi-objective view of algorithm designs. We want algorithms which are the best across all the instances. Can we have that? So here we see an algorithm which kind of does that, whereas the other family of algorithms is failing to do that. You would need to somehow specify how to choose this hyperparameter in a clever way, figure out based on the statistics of what to do. It's complicated business. It's not so simple to do. All right, so some questions about this figure. So YM is larger, expected regret will be larger. What is specific? I don't understand the second part of the question, but I can explain why the graphs look the way they look. So here, delta is, we are in a two-arm bandit setting. There are two arms. That is the optimal arm, and it has some reward. And so the reward of the optimal arm is naturally higher than the reward of the other arm. So the action set has two elements, A and A star. And delta is the gap between the two. And what happens is that if you have a very small gap between the values of the actions, then it doesn't really matter what you do. So the very small gap is uninteresting. So that's like the zero regret case. That's the thing that we already discussed, right? Because then the two actions have the same reward. It's not interesting what the algorithms are doing. If the gap is of a certain value, it's like you have a certain horizon, like, I don't know, 1,000 or something. So if T is like 1,000, then this horizon is the critical gap is going to be approximately the number of arms, so in this case 2, divided by the horizon. Because this is like the level of accuracy with which you can estimate means. When this happens, then the regret is expected to be the highest. And when the gap is of this sort, of this type, it will be really hard to decide which algorithm, which arm to choose. In this case, you want to have a lot of exploration. So here you want a lot of exploration. Explore like crazy. And if the gap is big, then it should be fairly easy to figure out which arm is the optimal, because your statistical uncertainty decays at a fixed rate, and there was a fixed gap between the arms, so the confidence intervals are decreasing at this 1/2 square root T rate. So very quickly you see a separation between two arms, and you can decide. So you don't need to explore a lot. Don't explore. And then we can come back to the graphs. So this ETC algorithm, it's called explore, then commit. Explore, then commit. Explore means that uniformly random choose one of the arms, one of the actions, and commit means go with the greedy choice based on the estimates. And so we can go back to this and we can understand what's happening here. So the algorithm with m equals 25 is going to explore for 25 time steps. And after that, it switches to exploration. And since it's exploring only for very little time, it's going to suffer a large regret in the critical region where exploration was important. It is under exploring there. So there's the blue curve. But the blue curve is going to do pretty well where you don't need to explore much. Where the gap is big, You don't need to explore much. This doesn't explore much. Exploration is expensive. You pay by giving up on reward. By choosing to explore, you're giving up on reward. So you pay for that. So in this region, since this algorithm is not exploring, it's doing well. Similarly, if we take the red curve, that algorithm explores a lot. Since it explores a lot, it's doing well in the region where you need to explore a lot, but in the region where it shouldn't explore, because the statistical uncertainty is easy to resolve, this a priori fixed way of like how much you want to explore is just bad. You're still exploring, even though you could have decided much earlier which action to take. So that should kind of explain it. I hope it does. All right. So we have this problem, like that in the lower bound, we had square root DSAT for the regret. Again, we see the number of state action pairs appearing. And if you want to solve a large problem, then this is highly problematic. So what can we do? We can use very functional approximation, and lo and behold, that's what people are also doing in online learning, but we're going to do it in planning first. So, all right, so let's get to this. So function approximation is a critical component of reinforcement algorithm, and this is the component that makes it possible for our algorithms to scale to large problems, and so it's hugely important. And function approximation, the way you should think about it is that it is just computation with compressed representations. So one lesson, general lesson is that the classical dynamic programming, so DP stands for dynamic programming here. So the classical dynamic programming algorithms can be made to work, but have really high demand for the function approximator. And then there are lots of like interesting things. So very often, like you have function approximator, you believe that it's a good one, but oftentimes it's not so great. And there is something called a misspecification error. So that's like how well this function approximation actually behaves on the instance. And maybe it doesn't behave that well. Well, if it doesn't behave that well, then we expect the performance to degrade. But it turns out that in reinforcement learning, performance degrades more than in supervised learning. So that's what I call misspecification error inflation. And one big lesson of the last year of research in reinforcement learning is that, or maybe 2 years by now, that this misspecification error inflation is unavoidable if you stick to polytime algorithms. Which you, I guess, have to. So another conclusion, which is very closely related to that, is that algorithms need to control the extrapolation error, unlike in supervised learning. All right. So how big is your MDP? So before we jump into like functional approximation, let's see some numbers. So the horizon on all of these problems that people probably have seen, right? Like there's a robot arm, and then like it has to solve Rubik's Cube. The next one, it's Atari games you have to play to the end and win the games. The next one is the game of the Go, and the very last one is a classic example of playing backgammon. So in this case, the horizon is at least 100, if not thousands or tens of thousands of steps, depending on the specific setting. The number of states in the various settings are estimated to be these numbers. It's a huge numbers. In the case of robot arm, it's a continuous state space, so it's like infinite dimensional, or infinite state space, not infinite dimensional. It's 60 dimensional, roughly, but it's continuous. So it's like you have to do something about that, because we have seen in lower bounds that algorithms that are prepared to, like, that need to deal with the worst case have to scale up linearly with at least, or if not quadratically, with number of states, depending on the setting. But then why do other algorithms succeed? Well, I say that experience suggests that having access to large computing simulators seems to be crucial. Therefore, we are in this planning situation, and also using functional approximation. It seems crucial because that's what you bias to, generality and flexibility. And now we're back to, like, how do you design algorithms? But generality and flexibility is one thing to look for. And then the big questions are they sufficient, and when, and which algorithms will work? So the setting that I will mostly talk about is online planning. So we have seen this. The planner receives a state, has to return an action, and this repeats. And so you just have to implement this getAction function. And the planner is judged based on how good the policy that this getAction function implicitly implement is in the MDP. And the other metric that we often use is how many queries the planner, the getAction function, how many times it calls the simulator, how many queries or algorithm generates when interacting with the simulator. So functional approximation is basically compression. So you have some huge state space, and you want to represent, let's say, value functions in this huge state space. And you need to compress them. And how can we compress these? Well, we're going to talk about specific techniques, but there is no way around this. Somehow we have to use compressed computation. And so you can compress value functions, and you can also compress maybe policies. And these are the things that are obvious to think about, and what people have thought about. All right. And so when you do this, what's interesting is that all the computation needs to happen with the compressed data. So you can decompress at a given state. You can ask, like, okay, what is the value there? This is my function approximator, but you have to update the compressed representation, because you cannot just list all the values because there are too many states. So even that is impossible in this setting. So the calculation needs to happen with the compressed representation. All right, so I hear that I have 30 minutes. Good. Well, I need to cut the cheese and get to the meat. So many times we're talking about linear functional approximation. And so what this means is that we have a bunch of basis functions. These are the phi i's. And you take the linear combination of these basis functions. These are the theta I coefficients. There are d of them. So you can collect them into a vector. And so here the point is that d is the number of parameters that you need to produce to be able to get a function that is defined over a whole state space that may have even infinitely many states in them. And so the number of parameters could be much, much less the number of states. This is an infinite wise compression. Then the question is just like, how can we use such a thing? So again, problem settings. You could have online planning with a random access simulator. And the new thing here is that you can ask for the feature, like you have a feature function that maps, let's say, either state action pairs or states to d-dimensional vectors, and you can ask from the simulator for the feature vector underlying a given state action pair. So these are the calls that you can make. The requirements otherwise are similar as before. Or you can have just like a local access simulator where you can only call this simulator on previously seen state action pairs. And in this case, the generator call, like you can't do this. The generator call just returns the feature vector for the next state, let's say. So the algorithm requirements that as usual, we want flexibility, effectiveness, and efficiency. Flexibility just means that we want the algorithm in this case to work with any feature map and any MDP simulator. Effectiveness is going to mean that the policy that is induced by the algorithm should improve if the fitness between like how well the feature map is fitted to the MDP improves. So graceful degradation, the name of the game. And efficiency just means that the runtime should be polynomial, regardless of the number of states. So polynomial in the horizon, the number of actions, the dimension, and the desired accuracy or suboptimality level. So what is this fitness? So fitness between features and MDPs could be measured in multiple ways. So one way is just to say that like this kind of expresses what you expect from your function approximator. So we haven't talked really about this action value functions, but we have the optimal value function, and we can have an optimal action value function. And the optimal value function is nothing but if you take the rewards as a function of the state action pair, you can collect them into a big vector, and then you can collect transition probabilities in a big SA by S matrix. So this is an SA by one vector, and then you can calculate this action value, optimal action value function. So this gives you the value of an action in the sense that if you execute that action in the MDP, this is the value that you would incur if, like the first step, you execute that action, and from the next step, you are acting in an optimal way. And if you know the optimal action value function, you know how to act well in the MDP, because then you just have to take the action which gives you the maximum action value, optimal action value at a given state. So it seems like a good idea to use features to try to approximate the optimal action value function. And so know the fitness between the MDP and a set of features or a feature map is going to be how well this approximates the optimal action value function. So this is one metric. Some other metrics are how well you can approximate the action value function of all the policies. So Q pi is also similar. It is just that here you, instead of V star, you plug in V of pi. So how well you are approximating the action value functions for the policies in the worst case, or how well your features are approximating kind of the Bellman operator or the structure of the MDP, in the sense that, like, if you apply the Bellman operator to a function in your function class, can you get a function which approximates well the fixed point of that operator? So that's another fitness metric, and then people proposed many. So effectiveness just means that, well, if this fitness metric gets better, then your performance drop compared to optimality should also get better. So the suboptimality should scale, and the examples of functions of the scaling are given this. And of course, you won't necessarily get this good, but if you exert a certain amount of effort, then there is a certain penalty that you have to suffer if the effort was not too big. And there, every quantity should be polynomial. So that's kind of like how you measure effectiveness. And so then you can have results for this classic dynamic programming style methods. For example, for policy iteration with linear function approximation, a simple case is when we assume that all the action value functions are in the function space spanned by the features, then what we have to do is that somehow we have to find a special subset of the state action pair. It's called a core set. So the property of this core set, and I do have some slides about it, but I'm afraid I won't be able to cover them. So the property of this core set, so I just say a sentence about it. The property of this core set is that the core set allows you to if you have good estimates of like the function values of a function that you need to approximate at this core set. So the core set is C, and C is a subset of the state action pairs. And if for every SA you have a good approximation to, let's say, Q pi, this Q hat is a good approximation to that, and you use your features to fit to these approximate values at this core state action pairs, then it has the property that at any other state action pair, the approximation error is not going to be much worse than the approximation error you have at these special states. So the extrapolation error, the error inflation outside of the special set is not going to be too large. And there is a nice theorem, the Kiefer-Wolfowitz theorem, that allows us to conclude is that if we had d-dimensional features, then you can always find core sets whose cardinality is not much larger than d squared. And so you can find finitely many state action pairs that allow you to represent everything, all the other state action pairs pretty well. For this, you just have to solve a least squares problem. And so then you can take policy iteration and then turn this into an approximate policy iteration algorithm, which would, in policy iteration, we were iterating through policies. You take a policy, you have to evaluate it. So when you evaluate it, you take the policy, you take the core set, and from every member of the core set, you use the simulator to generate a number of trajectories. And along the trajectories, this is called a rollout. You're rolling out with the policy. And you do this, and you truncate the trajectory. You have discounting, so you can truncate it, and you're not committing much error. And you get all these rewards. You sum up the rewards. You do this a bunch of times. You take the average return that you obtain this way, and that becomes your Q hat. And then you run a least squares fit, and that gives you some parameter vectors, a theta hat, using which you can approximate Q pi for the current policy pi pretty well. And after this, what you have to do is that you just calculate the greedy policy with respect to this action value function, and you can do this on the fly, on the demand, and you don't have to store the policy, but like you can just write a little subroutine that would do this, and then you just feed that with theta hat, and then for every state, that subroutine can just like return the action that maximize this expression, right? And so there's the implicit greedy step, and then you iterate this a couple of times, and that's the whole algorithm. It's very simple. And you can prove that this algorithm gives you everything that you wanted to have. So in a nutshell, if you're careful about how you're controlling extrapolation errors using a core set like I explained, then you can make approximate policy iteration work for you in this setting where the features are strong enough so that the approximation error induced for approximating the action value functions of the policies or any policy is not too large. There are other interesting lessons, and you can ask me later if you're interested in those. So interestingly, there is an inflation of the the approximation error or the misspecification error. And if you want to have a lower inflation by the square root d times h factor, then you can have that, but the algorithms that achieve that are kind of like slower. So their optimization error decays at a slower rate. And then those algorithms are similar to natural policy gradient or PPO. So people might recognize those. And for the classic approximate policy iteration algorithm with this least squares form, the inflation is provably higher. So even in the limit, this algorithm can suffer a higher cost due to misspecification errors. So it's in this way less desirable than the other algorithms. So maybe that explains a little bit about why this conservative updating algorithms are reasonable algorithms, and why people keep finding also in empirical experiments that they're working better than if you just run something like least squares policy iteration. So you can also come up with a variation of the value iteration algorithm that uses function approximation, and this is going to work well if you have this closeness condition, which just says that, like, the simplest of this closeness condition is that the image space under the Bellman optimality operator is a subset of your function space. So whatever function you take, you apply the Bellman optimality operator to it, it maps it into your function space. So linear MDPs or low rank MDPs are what make this happen. So they're a special case of this. And a slightly more general condition is this closeness condition, that if you take some function in your function class that you can represent with this finitely many coefficients, you apply the Bellman operator to it, and you get back into the function set. And if this is the case, then similar least squares ideas as here can be applied to value iteration, and you can get very similar results to what apply to policy iterations. So you can get this least squares value iteration algorithm, whereas here you had least squares policy iteration. And so this algorithm is similar to DQN, and so maybe these conditions shed some light on under what conditions you can expect an algorithm like DQN to work well. All right, so these were algorithm-oriented analysis. So I can't go into these beautiful results, G-optimal design, and so on and so forth. But I want to switch to the last topic, which is, what if you're a little bit more ambitious, and the previous results were about a case when we sort of assume that the function space is rich enough so that it can hold pretty much all the action value functions in the case of policy iteration, and in the other case, the case of value iteration, it was closed, and this seemed to be pretty strong assumption. So would it be possible to design algorithms which have similarly nice polytime bounds and similar behavior to the previous cases when one only assumes that, let's say, the optimal action value function can be well represented by the features? So that's the first topic. And it turns out that, unfortunately, the answer is that unless you know something else, like that you have a few actions, in which case we don't know what is the truth or not. But if you can have as many actions as you want, exponentially many of them, then you can prove that no algorithm can get a polytime result. So there is, for the planning setting, there is an example that shows that no matter how you choose an algorithm, you can always find some finite horizon problem, or you can also do it in discounted setting, such that if the algorithm is guaranteed to work well, it returns a data optimal policy, then with a constant data or whatnot, with high probability, then it has to use at least exponentially many queries, exponentially in the smallest of the dimension and the effective horizon, at least on one instance. So it's a needle in a haystack proof that one uses, but it's a pretty elaborate and tricky proof. So I'm not going to be able to explain much of the details. References are provided at the end of the talk. So the construction is based on building a tree and sphere packing results, which is used these days a lot for proving lower bounds, which says that you can squeeze in a lot of vectors on the surface of the D ball, the unit ball, which are nearly orthogonal to each other. And that kind of creates a needle in a haystack situation when you want to learn about, so these are going to be the feature vectors, and you want to solve this extrapolation problem that, okay, I know the values at few of these feature vectors, what are the values at the other ones? If there is some, the linear combinations that I'm learning about, but if these are nearly orthogonal, then there is very little information that you're gaining this way. And you need to basically try all of them. So so that's the essence of the construction. You might think that, okay, V star is also going to be similar. It turns out that for V star realizability, when the optimal state value function is linearly realizable with some features, and we also know that there are only a few actions, then we have an algorithm which is at least provably query efficient. So the number of queries that it uses in each get action call, this algorithm, is shown here. It's dh over data to the power of a. And so if a is like 2, then like this is an okay quantity. If a is big and you're thinking about a is scaling, then this looks really scary. This is exponential in a. So that's why if you want to phrase this as polytime result, you have to say that, well, a is constant, right? So for a constant a, you can have a poly query cost, but this exponential dependence on the a is there, and the algorithm itself is not known to have a polynomial time implementation, but the algorithm is still pretty interesting. So it uses, interestingly, an optimistic parameter choice, and it uses rollouts to check for consistency. So it's a TD error, there's a temporal difference error. I didn't talk about the temporal differences, but the temporal difference error is nothing but by looking at the difference between, you have a test. Okay, so in this case, it's V functions, it's state value functions. So you have the Bellman operator, you apply it to your function, and you look at how much did it move. So these differences, it's like a vector of differences. These are the TD errors. And so the algorithm checks for these TD errors, and if it sees big TD errors, then it rejects the underlying parameter vectors. So these functions are parameterized, so they're compressed, that they have this d-dimensional parameter vectors. Then it rejects that, and it kind of shrinks the hypothesis space and then chooses optimistically again, and it iterates these things. So it's kind of interesting because it's close to dynamic programming, but it's not quite dynamic programming. Of course, it's still based on value functions, but optimism plays a crucial role. All right, so this was problem-oriented analysis, and this is in a nutshell how much Well, there are a lot of other results about this very functional approximation, but these are kind of like some core results about this. And again, references are going to be provided at the end of the talk. So I'm gonna skip these slides and just switch to switch gears and final topic, batch reinforcement learning. So here the big lesson is that if we talk about minimax regret and data collected by following some policy in an MDP, then there is an exponential lower bound. And so this setting is as follows. The algorithm is fed with some data D, which is a sequence of 4 tuples, such that the S prime is obtained from taking action AI in state Si, and this is the next state, and this is the reward along the way. This is the data that you feed the algorithm, and we say that this is policy induced if the AI is equal to what a policy would choose at that state, and then you can have a bunch of these trajectories. That's the input, and the algorithm still needs to return a good policy. So that's the setting. And the theorem just says that, well, bad luck. If you have this policy-induced data, then for whatever logging policy you choose, for any constant probability data on the algorithm, there is at least one example on which, one instance on which this algorithm, which is sound, is going to need this many observations. And so here, this scales exponential with the smallest of the number of states and the number of actions. So the number of states in the horizon. So if horizon is big and the number of states is big, then this is kind of a doomed enterprise from the perspective of controlling minimax regret. The construction is a simple chain. It's a little bit different. It's a combination of the coin flip argument and some structure needs to be brought in. But the point is that you can create some situation where the critical information comes late, and you only see that critical information if along a chain you kept choosing the action, and you choose these actions in an adversarial fashion to be the actions that are least likely to be chosen by the logging policy. And then if you do all the calculations, then you get this exponential lower bound. So the open questions here: what's a good way of evaluating and comparing batch algorithms beyond the worst case? Can we use, for example, something like adaptivity? And it turns out that no, you can't. A lot of people are betting on the pessimistic algorithm, and that's studied in many fields and many different names, and addresses the winner's remorse, and it's known to be weighted minimax optimal with a certain weighting. And so a lot of people are really excited about this, but as far as I'm concerned, it is still a question to me whether there is life beyond the pessimistic algorithm, or like we didn't. I haven't seen yet a very clean argument of why the pessimistic algorithm is something we should care about. Oh, just in a nutshell, what the pessimistic algorithm does is that it's the opposite of the optimistic algorithm. It collects the samples, estimates the MDP, and takes the MDP, which gives the worst possible values, and then computes the optimal policy for that MDP. So it's acting in a pessimistic fashion. And yeah, it's kind of obvious that if you do this, you're acting pessimistically, you can only positively surprise yourself. So address is the winner's remorse, that's pretty self-evident. And the algorithm also has this nice property that it only needs the data to cover where the optimal policy would go. But I have some problems with this as well, because how would you be able to generate such data? Most of the time, I think that we can't generate data such that the data will cover where the optimal policy will go or where good policies are going to go. We don't know how to control, how to generate data in a nutshell. If we knew, then like we wouldn't really have this problem to start with. All right. So in summary, I think that a very valuable viewpoint is that reinforcement learning is should be studied with tools and techniques of computer science. We should talk about algorithms, instances, and like how they relate to each other, how to solve this multi-objective optimization problem, which is to choose good algorithms that work on all instances. And foundations, strong foundations are provided by just looking at MDPs and planning. And we talked about online learning, functional approximation, planning, batch RL, lots of things. I think it's good to stop here. I already shared the slide. There are some references. One basic reference would be these lecture notes that I'm still writing. This was a lecture series I gave at the U of A in this winter, this year. But I can also recommend the lecture notes of these folks, Alek Agarwal, Nanjiang, Sam Kakadi, and Wen San, which is accessible at this URL, and the RL theory virtual seminar series have already been mentioned, and like more and more and more references. Okay, right, let's stop here. All right, so quick Q&A, I guess, because we're running low on time. I just finished 1 minute late of the set time. So we can probably have, I don't know, 20 minutes of addition for Q&A or 10, I don't know. Anyways, the first question that I see in the chat, are there any interesting research problems or applications where environment is not modeled as MDP? Yes, I mean, MDP is fairly general. One thing that was probably not too clear, and I was sweeping it under the rug, is that in the MDP framework on its own doesn't really talk about observations. And in any application that one can think of, you can apply MDPs by thinking about the whole history as the state, and then you observe the state. But that viewpoint brings with itself an explosion of the state space. Well, in reinforcement learning have all these wonderful tools that tries to deal with that. So maybe that's kind of already taken care of by using very functional approximation or whatnot. But I suspect that that's not completely true. So if we start to explicitly model that the states are not observed, so one very simple extension of MDPs is PUMDPs, where the interaction between the agent, learner, whatever entity, and the environment is such that the agent sends an action, the environment reacts by changing the state according to the MDP transition dynamics. So there is an underlying state, but that state remains hidden or latent. And then observation is spitted out, which is a stochastic function of, let's say, the current state and the last action. And that is what is communicated back to the agent. So that is a richer framework that covers more than MDPs, strictly more than MDPs. And it is, at minimum, we have to investigate under what settings we can cover problems, these MDP problems with the tools and techniques that were described in this lecture. And there is a lot of wonderful research going on in this topic. Other than that, I think MDPs are fairly general. Sometimes people bring up non-stationarity and like other variations. Okay, so one thing about MDPs is that it's like it has single rewards, and so maybe that's not a good choice. A lot of applications, it's much easier to describe them with having multiple objectives, multiple reward functions or cost functions or whatnot, and then trying to resolve the trade-off between these. So that's an extension that I think is worthwhile being studied. And maybe I stop here because I think that you can think about many other ways of extending MDPs and going beyond MDPs, but maybe these are the most important. Can reinforcement learning be used for PAR prediction? PAR usage prediction, I'm guessing, maybe that's the question. So there are two parts to this question. So first of all, reinforcement learning, mostly when we talk about reinforcement learning, we are thinking about solving control problems where we are choosing actions to control an environment so that in the long term, something nice happens. And PAR prediction doesn't seem like a control problem, but in reinforcement learning, we have this sub-problem of value prediction. So we need to predict the long-term value of policies. And so we are developing all kinds of algorithms to do that. And I can think about that for PAR prediction, you could try to formulate things in such a way that reinforcement learning becomes relevant, even just for predicting future power consumption or whatnot, because it has this temporal aspect. So the reinforcement learning algorithms are really tuned to this temporal aspect of these decision problems. And the value prediction part is really tuned to that as well, and that seems relevant. All right. Other questions? Thank Jane saying nice things about the lecture. What are your thoughts on using self-supervised learning to improve the sample efficiency of reinforcement learning? Sure, go for it. It's important to point out here is that reinforcement learning, in my point of view, is a set of problems. It's not a fixed set of algorithms. So if you take, like some known reinforcement learning algorithm, you add self-supervised learning on the top of it, or you do self-supervised learning in conjunction with it, then you get a new reinforcement learning algorithm. And that's totally legit. I think that the challenge in applying self-supervised learning in reinforcement learning is that there are so many things in the world that you could think about learning, and not all of them are equally valuable when you are resource bounded and you want to solve a task. So the key question there is to decide and design experiments, design algorithms which are clever about this resource allocation problem of how do we decide about what to learn about. So sometimes, okay, we know a lot about these environments and we can decide as designers of the algorithm what's good to learn about. So for example, in the robotic application, maybe one should use self-supervised learning to learn about vision. It's gonna be the same no matter what the robot control problem is. It's like you have the two eyes and the signals are the same, the regulators in the world are the same. Of course, it's a no-brainer, you should use it. So I think that it's a good idea, but these are the challenges. So next question, what is open question I'm excited to see solved? Well, there are a bunch. So if we just go back here, well, okay, this open question is interesting, but it's a loose open question. But if we go back to just this planning, results. For Q star, realizability, and the many action case, we have impossibility. So there are two dimensions, Q star or V star. Which one is realizable? And the other dimension is, okay, how many actions do we have? So that's the other dimension, number of actions. So if we know that the number of actions is exponential, then this is impossible. We also know that if you have just constant number of actions, then this is possible, although we don't know whether it's polytime. So that's an interesting computational question. But we have no idea about all these other rubrics here. I think that's a beautiful question. And I think that in general, this PAM-DP world is also quite nice. The multi-objective is also, like, I'm excited about a lot of things. How to consider when to use reinforcement learning? What is the advantage of RL compared to supervised, unsupervised learning? Well, the advantage, I would say, is that it solves a different problem, right? So if you need to figure out what actions to take and you didn't have any supervised learning signal for that, then you just like have to solve the search problem together with the learning problem. And that's the topic of reinforcement learning, right? So that's the exciting part. It's like being clever. It's an inference, like in RL solves an inference problem. It's defined with an inference problem, what action to take. If you have these pieces of information about the environment, like transitions and rewards, you don't get a solution ready-made for you. Like in supervised learning, you have to figure that out. It's a different question. So I think that reinforcement learning is also often used in situations where it's like competing with supervised learning. And you can try to do that, like NLP and whatnot. That's really interesting to me because you can transform a lot of questions into inference questions. And then once you have an inference question, then you can turn that into an optimization question. You can turn that into a sequential optimization question, and then you end up with a reinforcement learning problem. And that's interesting. And I was surprised to see that in some challenging applications, reinforcement learning seems to be pretty much stood out. All right, so someone's asking, how can you contact me? Well, I'm on Facebook, on this Facebook group, and you can write email to my email address, which is here. And I think that's it. I think if you want to ask a question, maybe it is a good idea to ask the question in the Facebook group, because the question, you might not think so, but it could be interesting for many other people as well. And here I also have to say that there are no bad questions. Like the only bad questions are the ones which are not asked. So be brave and just ask questions there. Okay, what do I think about building a strong AI using reinforcement learning? I think that that's our best bet currently. So for example, okay, so here's why. So this result, this exponential sample complexity result, what it tells us is that kind of supervised learning, which just sits there, waits for someone else to collect data so that we can reason with the data about what actions to take in the world, is kind of a doomed enterprise. I think it's really dubious whether you're going to have the right data if you need to take action and you have to reason about the consequences of taking not only one action, but chains of actions. what do you need to build AI? I mean, like, it's no question that decision making and sequential decision making is in there. So I think some part of this reinforcement learning need to be there, and learning has to be there as well. Because we have a hard time of specifying what does it mean to have strong AI. So our best bet is that we just like create learning problems, and then eventually the algorithms figure it out. David Silva claimed that ARA could lead. Well, ARA could lead is not, what do I think about that? Well, I know Dave very well, and I think that he may be right. A few things I would challenge. So one is the single reward hypothesis, which I find increasingly dubious to work with. I think that that's a weak link, but maybe the patching that needs to be done on the top of reinforcement learning is not too large to worry much about that. The other thing is that I think that we are pretty far from being able to pull this feat. I feel that there are many missing elements of the puzzle, but since in the past we have been surprised by how good the algorithms can be, I think that Dave is optimistic because of that, or I don't know whether he also put some numbers there of like when he would expect this to happen. Because like if you take it like to the extreme, like it happens in the indefinite future, then like it's a very weak claim, right? So yeah, I don't know.
Okay.
Again, yeah. What?
Okay. I have a question. The machine learning summer school staff wants me to ask this question. Could you give some advices to students interested in machine learning theory in general?
General advice?
Yeah.
Read books. So go for the books. And the reason I say that is because it's really hard to pick up a good base from reading current research papers, but don't get lost in the wonderful world of the books either. So kind of like target a few books, keep reading them. This has to be going on for a while, and just like, you know, regularly just like go through one other book. And at the same time, also think about research problems, and don't shy away from thinking about problems that look simple. Pick problems that look exercises, and they will grow into something much bigger than you would think they are very easily. So I often found this to be a very useful strategy. In the worst case, you solve an exercise, it was just an exercise, and then you didn't waste a lot of time on it. But a lot of times, like once you start thinking carefully about something, it turns out to be more interesting, more challenging. So just don't shy away from, and if you, yeah, like if you think that there is a gap in the literature, it is very likely that there is a gap. So just go for it.
Okay, your advice reminds me of a question asked by a student. The student asked, could you recommend that textbook for online learning and the bandits that you just talked about? Is it okay to just recommend the bandit book that you co-authored? Yes, this one.
Yeah.
Okay.
It's hard to see, but it's on my webpage. The PDF is free. But everyone should also buy the book, but actually not important. The PDF is there for everyone to take. And I think for Bennett's online learning, this is a good start. There is the book by Niccolo Cizia-Bianchi and Gabor Lukosi, which is a different sort of online learning book, Learning Prediction and Games. That's also a pretty good book. And the lecture notes that I listed at the end, they're also pretty good.
Okay, I think the book Csaba mentioned by Csaba Lugosi et al. Is Prediction Learning and Games, published by Cambridge University Press in 2006. Okay.
Yeah.
Okay, thank you, Csaba. Okay, now the session ends. Everyone, please notice that there will be an industrial talk from Google and a lecture by Professor Shentian Lin in the afternoon. Okay, thank you, Csaba.
Thank you. Bye-bye.
Bye-bye.
Take care, everyone.